Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives.
In this episode, we are talking to Anastasia Athanasiou, a postdoc fellow in structural and wind engineering at Concordia University, about performance-based multi-hazard design of buildings. I'm your co-host, Matt Picardle.
And I'm your co-host, Kara Green. Now let's jump into our conversation of the week with Anastasia.
This episode is brought to you by PPI, a leader in engineering exam prep for the PE structural exam. PPI provides expert prep courses and study resources designed to help you pass the PE structural exam the first time. PPI's PE structural course is fully updated and taught with October 2021 code references and includes new editions of their PE structural books. PPI's live online course includes hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. Check out PPI today at ppi2pass.com to see all of the options available for FE and PE exam prep.
Anastasia, first, thank you so much for joining us on the show. We are so happy to have you.
Thank you for inviting me. It was a great pleasure. It's a great pleasure to be here.
Perfect. So in your own words, can you tell us a little bit about what you do on a daily basis?
Okay, so a few facts about me. I'm Anastasia, and I'm an international postdoc researcher at Concordia University at the Department of Building, Civil and Environmental Engineering. It's Montreal, so it's Canada, Eastern Canada. So I'm a morning type, so I wake up quite early at 6 or 7 o'clock, and I have my Greek breakfast. And then I ran to the university with the metro, and I start my day at the wind lab, because since I'm a postdoc in both structural and wind engineering, I was assigned an office in the wind tunnel. And there I spent most of my time in front of my computer. So during the first years of my postdoc, I would normally develop numerical models in OpenSys and around them. But since it's already my third year here, I'm mostly focusing on collecting data and writing papers. And it's super nice because I have very awesome lab mates that are wind engineers. So I can have these very nice breaks where we talk about wind engineering, and they are most experts on that. So I can get a lot of input on wind engineering, wind tunnel experiments, and also CFD, computational fluid dynamics. So I spend most of my days at the wind tunnel lab. Yes, like being a postdoc is quite engaging. We have flexible programs, so that means a lot of work. But also, now due to COVID, we can also work from home. So I'm having this podcast from home. So it's fun. It's nice.
Awesome. Thanks for that. And I know in 2017, you were invited to present your work to the first Japan-Greece International Workshop by young researchers on advanced materials and technology for applications to steel and composite steel concrete structures in DPRI Kyoto University. Yeah, I got that right. Can you tell us what you presented there and how that experience has benefited your engineering career?
Yes, for sure. So that was the third time I went to Japan. I had visited Japan before twice for International and Asian Conference on Earthquake Engineer. And in fact, I was there on March 2011 when the big earthquake happened. And I wasn't supposed to be there in 2017 because before I used to go there with my Italian supervisor. I did my PhD in Italy at the University of Catania under the supervision of Professor Oliveto. But I had a colleague who had been to Kyoto University, and she had met this young Greek professor, Dr. Skalomenos. And when he heard about me, and he knew other people in Europe and in the States, he decided to organize this mini symposium that was Japanese Greek symposium on earthquake engineering. So I went there, and at the time I had 7 years of experience in Italy as a research assistant, as a PhD student. So I presented my work that was on earthquake protection systems. So the things that I presented there was essentially a big part of my PhD work. So during my PhD, I was working on data collected from full-scale free vibration tests that were performed on a real building in Sicily. So during this test that happened in 2013, a real building was pushed to initial displacement. It was not very big, it was 10 or 15 centimeters because we didn't want to damage the building. And then it was left to oscillate. And we had a great amount of data. And as a PhD student, I did the signal processing. I used the data for structural identification, that is to identify the properties of the structure, validate the design, verify the numerical models. We had developed with the research group of Professor Oliveto. So I tried, in my small 30-minute presentation to present all this knowledge I had collected in Italy. And it was a great opportunity because it was a small event. So we had the opportunity of meeting with senior and earlier senior and junior or earlier career researchers there and master students. And how organized and efficient the Japanese are, especially in how professional. So we got the opportunity to visit some sites at Kyoto that had been affected by the big 1995 earthquake. We went to see how a company, an industrial company works, a structural firm works in Japan. And we also had this lab demonstration. They have a very big laboratory where they do shake table testing of earthquake resistant systems. So it was awesome. I met a lot of people, I interacted with them, I had fun. I went back to Japan, I ate delicious food, and yes, I expanded my knowledge and my network. Yes.
Oh, that's really cool. Yeah, I think what's cool about that is you spend all this time gathering data and all this research, and then now you get to present it to not only to a more broader audience, but international audience, but also Japan, where they frequently have big earthquakes. And I know they have a lot of earthquake research over there too. So I think that's really cool. And I'm sure they learned a lot from that. And like you said, I'm sure you learned a lot from them because of their extensive practical experience with earthquakes. Yeah.
Yeah, yes, that was awesome. And I think that's the best part when you go to a conference or any kind of symposium, you have the opportunity to get feedback like from younger and senior people. So it's very beneficial for your career because like many more people than we think in the world, in the planet, maybe they are working on the same thing and have the same questions or have the same problems in their research, and you can benefit from their questions and their feedback.
Yes, most definitely. And it's something I always enjoy going to conferences because it does allow you a breadth of range, especially in the networking industry. You meet so many new people, and exactly what you said, they provide feedback on some of the stuff that you're already working on. But I wanted to touch on something because you brought up, of course, earthquake, and you're working on wind tunnel testing right now. So in relation to earthquake and wind actions on a building, what are some of the similarities as well as differences between wind and earthquake loads and how they act on a building? This is actually really interesting for me because I'm currently working on a project and we're tying in together some ductility and how it relates to both wind resistance and earthquake resistance. So I'm interested to hear your feedback.
Okay, so both earthquake and loads are lateral loads. That means that we apply them as horizontal loads that act on the structure. And usually when we have small to moderate buildings, then we can assume that we can model them as equivalent lateral forces. Okay, this is only valid when we have smaller structures, because when we have very complicated structures, of course, this doesn't work out. And when we have earthquakes and winds, these are accidental actions. So if we have a site, a building or a bridge or a structure that is in Canada, in Montreal or in California, LA, we shouldn't expect that they are subjected to the same hazard. So we have different events, different forces according to where we are and according to what building we have. So the geometry, the shape, the flexibility of the building is really important. So the next stage is differences, because maybe there are more differences than the ones that we are actually consciously aware of. So wind is essentially applied and conceived as an external force, right? So what we have is a wind blowing and hitting the building. And the way we simulated what we have positive wind pressures that act on the windward surface, and on the leeward surface, we have negative pressures. What happens on the side and the roof, there the phenomenon is more complicated. We have non-uniform distribution of forces, okay? While on the other side, we have earthquakes that are mostly perceived as internal forces. So we have the earth shaking. So what happens is the earth can shake in any direction. So we have 6 degrees of freedom. We can have 3 translation, horizontal, vertical, and 3 rotation. So there's a lot of research on the rotational components, but usually what we consider are these 3 translation degrees of freedom. And for small structures, ordinary structures, we wouldn't even bother for the vertical component of the earthquake, because if we have designed properly our elements to sustain the gravity loads, then we just focus on the lateral earthquake loads, right? So the way we perceive earthquake is like inertia, and earthquakes depends on the mass of the structure, on the stiffness of the structure, and the acceleration on the earth. On the other hand, as we say, for wind, we have pressures, we have external forces. So in order to get the wind loads, we will multiply these pressures, that act on the surface, on the wall, with a tributary area. While these wind loads, of course, they depend a lot on the environment. So it's important if our building, if our site is next to the sea, or it's say in Times Squares in the downtown. It's also very important how tall the building is, if there are openings in the facade. So it's environmental, it's geometrical factors. Let me see if I forget everything. Yes, and it's also very important what is the velocity and the direction of the prevailing winds. Now, other things that are important are the intensity is different. So how do we describe the seismic intensity? We reason in terms of peak ground acceleration, right? While for wind, we reason in terms of velocity or velocity pressure. Also, how do seismic recordings look like? The seismic recordings are usually acceleration time histories. So what we have a random signal that oscillates around 0. So if we put this signal in our numerical program and excite the model, what we will get a response that goes up and down. So if we try to visualize it, what we will see, we subject the frame to an earthquake. So we will see the frame bending back and forth. And if we try to read the force in the member, we will see, for example, say we have a brace, it goes to tension, it goes to compression. So we have cyclic loading. On the other hand, if we go and look for a wind recording, the one like my lab mates take from their wind tunnel test, this is a time history of normalized pressures, okay? And it's very long. A wind can last for an hour or more, while an earthquake lasts for 30 seconds. Say in Eastern Canada, it can last for more in Victoria, in the Pacific coast, or in Japan. So the wind component has a very strong static component, so the mean is not 0. And the static component causes the building to move towards one direction, so we have a change of the equilibrium position. And then we have the gustiness, that is a gustiness that we also see in the earthquake. So this gustiness is responsible for this elastic and inelastic excursions around the displaced equilibrium position. So we would describe the wind loading as a monotonic loading. And then the last two things, earthquakes cannot be predicted, right? While for wind, we have early warning systems, but in line of principle, they cannot be predicted. While wind loads, if we study the meteorological data and we talk with wind climate scientists, we can have warning, we can predict them. Then how do we replicate earthquakes using shake tables? And if we go, say, to the E-Defense, some big facility, we can even have tests on full-scale elements. We can say, how do you say, a big column or a one-by-one house or building. While if we want to replicate some wind excitation, we go to the wind tunnel, and there we test cities or small or buildings that are scaled 300 or 400 times. So imagine we don't account for any flexibility of the structure in the wind tunnel. So yes, more or less this is all.
No, and that's a great explanation, especially because I know a lot of engineers, they take into account both different types of loading, especially you mentioned you're up in Canada. I know Canada has a lot of earthquakes, or take into account a lot of seismics, but they also take into account winds because y'all do have, of course, what am I trying to say? Coastal regions.
Yeah.
But I know I remember wind studies being a big deal. I think it was with ASCE, was it 716, the update to the new wind codes?
There were
Do you remember, Matt?
updates on the 716 for sure. Yeah, definitely a lot of
Yeah,
wind changes or modifications. So it's
yeah. So
still going. Yeah, lots to learn.
yeah. Yeah, so it's great to hear that there's some kind of studies that are going on to compare the two, but also to explain the difference fairly clearly.
Yeah,
Okay.
well, I was gonna ask though, because I know there's a lot of research on wind and they're getting implemented in our codes for structural design. And like uh, like Kara just said, there was like a new update, at least in the ASCE 716 codes, and a lot of wind changes. And I'm sure those were based on research as well. What are some of the latest challenges that you still see in wind design uh, that you're working on, or you guys are still trying to solve that maybe could be implemented in further codes?
Well, totally, there is a lot of work to be done in wind engineering also because it's a, say, younger principle than earthquake engineering, right? So in earthquake engineering, we have all this knowledge from observing natural hazards like happening and seeing the results, and also by having many research working on the subject. So for sure, a nice thing that I noticed by looking in the literature is that most major international codes, and when I say major, I mean North American, the US, the Canadian, New Zealand, Japan, Chinese, and European, they have the same prescriptive strength-based design approach for wind. So there are small variations on the way we define the velocity, the way they name coefficients, but the logic, the rationale is always the same. So we have a structure and we consider the service level and the strength base level. And for the service level, that is when we have very frequent winds, because you know, winds are more frequent than earthquakes. In fact, if you go outside, it's more possible that you feel the motion of the wind blowing against, you know, your bike or you than an earthquake. So for very frequent winds, like 1 in 1 year, 1 in 5, or 1 in 10 years, what we don't want to have this discomfort, right? So what the code says is that be careful for the drifts and acceleration, limit them when you have very frequent winds. But when you go to the strength level wind, that in the States is 1 in 700 and in Canada is 1 in 500 years for ordinary structure, they say, look for this level, design for this wind base shear, distribute the shear along the height of the structure without considering the inherent overstrength of the structure and the ductility of the structure. So imagine how expensive it is, this kind of design, and how conservative it is. Because if we are in areas where we have multi-hazard, from the one point of view, we have the super efficient, super refined, performance-based seismic design for which we can do some enhanced detailing of elements and take into account ductility. And from the other point of view, we have this very conservative, old-fashioned, strength-based wind approach. And there are reasons for that, right? Because winds are complicated. It's not easy to have wind recordings and so on. So it's totally okay that it is like this. But it's the time, you know, to move on and have this transfer of performance-based seismic design to wind. Like, so this is the major challenge, take into advantage the ductility of the structure, the inherent overstrength in order, you know, to enable a cost-effective design and anticipate damage. Yeah, so we want to optimize this. This is the main challenge. And I have to say that in the US, researchers and the government is doing a great job. In fact, in 2019, the American Society for Civil Engineers issued a very nice pre-standard for performance-based wind design. And most researchers that work in multi-hazard, they make a reference for the wind part to this document. So yes.
Yeah, I know that's I've heard of that one with it was like a new manual on wind performance-based design, and it's new. And I know we've been doing that a lot lately with seismic, but for wind, I think the industry is kind of realizing, hey, we do this for seismic, but like you were mentioning, it's kind of inefficient if we're doing that for wind at the moment. What else can we do to maybe make it a better analysis and maybe essentially a better design, better engineering for wind cases? And
Yes, yes.
yeah.
And what I wanted to add, just to be fair, it's not that we have many good seismic engineers and we don't have good engineers. It's nothing like that. It's like the wind phenomenon is more complicated. So imagine an earthquake record has how many points? 2,000 points, so it's a short record. And we know we have strong motion databases. So easily a practitioner who has a master or even a bachelor in engineering and is interested about dynamics, they can perform a simple analysis in half an hour, maybe less or more. But for wind records, we don't have wind records, and like we need to conduct wind tunnel experiments. And an individual, a practitioner without prior knowledge, you need the expertise, you cannot do them themselves. But even when you conduct the wind tunnel experiments, they will give you some pressure coefficients that they measure on the surface through pressure taps of the buildings, and you will have and integrate them into wind, corresponding wind forces. So you need the expertise there. And also wind analysis, especially if you want to do them in the nonlinear range of response, because you have 1 hour of data. They take time. Of course, as technology advances, yes, we will be doing like wind analysis, maybe through parallel computing and completing them in minutes. But now it takes hours if you want to have convergence. Yes, so there are these more obstacles that we are trying to overcome in order to advance the state of practice in wind engineering.
Yeah, and that's great to understand. I remember going to a discussion. It was done by a firm in Houston. And in Houston, because we are along the coastline, we get a lot of hurricane winds. And I remember they were building a new structure, and it was a government structure, and they had to do a full wind analysis before they could actually construct the building. And it was really interesting to kind of see the process, because I think that discussion came around in 2018, and it had just after the ASCE 716, the wind loads had increased. And so wind was a hot topic then, but in Houston, wind is always a hot topic.
Topic and multi-hazard engineering. So I want to give this small advice, because I come from Greece and Italy, and I've been studying for 10 years for earthquake engineer. Also, if you are looking for positions, because in the end, you have somehow to translate your knowledge to a job, right? Choose for a field that is more popular. And nowadays, natural hazards other than earthquakes, they will help you get a job. Look what's happening. Look at the weather climate. We have more floods, more storms, hurricane, excessive phenomena. So choose for a discipline, that probably will give you a job. Yes, we know much about
job security.
For a good seismic engineer, and if you have studied something, you have made your mind, how to do research. It's not that knowledge that is thrown into garbage. It's also so useful. But this is something that I understood. We have to be flexible. I started as a seismic engineer, and now I'm specializing in wind. And I noticed that now my job gets more attention and more experience and more, exposure. And I get more opportunities to talk about wind and multi-hazard than I got as a seismic engineer. So that's a small advice. Seismic engineering is cool, but go also for modern ones, other hazards. Yeah.
No, that's great advice. And, me and Matt have talked before about like who listens to this, and everyone is always open to learning more about opportunities that are becoming available in the market. So that's great advice to our listeners. So I'm going to pivot a little bit about, your experience with earthquake engineering. So why is it so important to do an earthquake risk assessment, and like what does that involve? Because you'll have to forgive me, I'm fairly new to seismic in Texas. We don't have very much of it, so I always learn from Matt or people who work in California, like the ins and outs. In Canada, I do work with some Canadians, so
yes. So why is earthquake risk assessment important? I think this is a great question, because it's a fortunate occasion because 2 weeks ago, I don't know if you know, the Conversation platform is an academic platform where early researchers or professors publish some short article about the hot topic. So I published something about the earthquakes and development on codes. And in my short article, I studied and I found out this fact. I found that in 2017, the US Federal Emergency Management Agency estimated that the annual cost of earthquake damage in US, of course, was $6.1 billion. It's a huge amount. And they also said that nearly half of the Americans are exposed to seismic risk. So why is this happening? Because as the years advances, we have more knowledge about where the faults occur or about the earthquakes. This happens because even though the developing world is aging, we're still experiencing a steady population growth of 1%. Right, more or less. This is the statistics in the 60s. And we have this urbanization. So we have a lot of people concentrating in the mega cities. Take Tokyo, it's a huge city. Athens, Rome, Paris, London, New York, Los Angeles, San Francisco, and so on. So we have more people being exposed to the risk. And unfortunately, it's an unfair world. It's first the marginalized, the homeless, and the vulnerable population that will be affected if a natural hazard occurs like that. So we need to protect them. And why is this happening and why is this important? Say that we even found a way to predict where earthquakes occur, in a parallel world, we could develop the perfect, without mistake, the perfect building code, but still this building code would be valid for the new structures because the building codes are not retroactive. So you mean what you build has to conform with the criteria of the code that is in effect the time that you build, you design and construct. So what happened to the hospital, the theaters, the schools, the buildings that were designed following previous standards that we didn't have of this knowledge? What happens to the cities that they were built in a site where we thought that earthquakes didn't occur, but then we realized that earthquake would occur? It means that these people, there is human life and property, that are in risk. But I'm sure that globally, the governments are making steps, but I think it's a huge responsibility and it becomes very complicated because I saw it happening in Italy and in Greece. Even if the government gives money to retrofit schools and hospitals, that's totally fine, and infrastructure, like bridges and so on. What happens with the private property? Should the government give money to the private owner to rebuild a structure that is ready to collapse? How do you convince the people, the individuals, to do it? So it's very complicated, but it threatens human life. It threatens the resilience of the society. So it's really risk assessment is fundamental. So the steps to the risk assessment, what are they? So the first step is to identify the hazard. What is the hazard? In this case, it's the earthquake. So we need to know at a certain site, is it of moderate, it is of small, or of high seismicity? So we need to have what we call the intensity measured, and it's the acceleration. So it's the ground motion shaking for an earthquake. The second step is, as a structural engineers, to do the structural analysis. So we need to have a good model, and a good model is a model that can predict sufficiently well the response of the building. We have a robust algorithm. And then what we need to do is we go in a strong motion database, we read the code and the regulation, and we go and extract the motions that are relevant for the site. And we excite the model with these motions. And what do we get? We look at the output of our Excel file, our MATLAB code, our SAP, tabs, or OpenSys. And usually what we look for are forces, are drifts, and acceleration. Sometimes these are called as engineering demand parameters, so the demand to the earthquake input. And once we have these demand parameters, we can go and see what is the probability. We can use mathematical model, fragility model, and see what is the probability that we will have damage given this demand in the structure. And according to this damage, we can have some variables that we call them decision variables and say, okay, we go to these demands, what do we do now and how do we decide? And now we are on what we call the second generation of performance-based design and assessment methods. So we want to decide in terms of socioeconomic variables. So how do we decide that something is harmful? If it takes a lot of time to repair and a lot of money to repair, we know that this is not good for the society and the stakeholders. So more or less, yes, this is what we do during a risk assessment. But of course, I wouldn't like that the students to worry too much, because these are things that you need to do a lot of reading. And if you go to a company, you will have a senior person that helps you and give you the FEMA readings. And it's a teamwork. You wouldn't have to do all these steps by yourself. So one step at a time. Yes.
And I want to say, like, risk assessments, this was, and Matt, maybe you can kind of weigh in. This was something that happened in California, where it's like every time that there's a renovation on a building that is technically non-ductile, they have to upgrade it to an earthquake resistant design. Is that correct?
There are laws in California where, especially for non-ductile structures like concrete structures or even soft stories, there are laws that require building owners to retrofit them. So I think that's at least one of the good things that we're doing, at least in California, to make owners more aware, and homeowners or whoever's owning the building to make them more aware. But I think that is one of the challenges. Relating to that, Anastasia, do you know how, I guess, because one of our challenges here in California is, or at least even in the US, I believe, is making the public more aware of these hazards. In California, we haven't had a big earthquake that like really damaged cities. I think the earliest one was like in Northridge, maybe that was like in the 80s or early 90s. So a lot of people here don't really know what it's like. They feel like if an earthquake hits, oh, most of our buildings are safe, like, oh, we're good. Like, so there's not really, everyone thinks everything's fine, but it's like, well, it just hasn't happened yet. The earthquake hasn't hit a big city. That's why it feels fine. For other countries, like where earthquakes are more common, like Italy and Japan, did you get a feeling of maybe a public perception of the earthquake? Is that different, or are they still, I guess, less aware of how important earthquake safety is?
Yeah, that's a very good question. So I would make the distinction between the westward, so Italy, Greece, South Europe, and States and Canada and Japan, because in the Oriental world, they have a very holistic view of the society, so they are very well prepared, and they were really traumatized by the latest earthquakes, and they are happening quite often. So we have the Kobe earthquake, massive earthquake. After that, we see base isolation and earthquake protection techniques being widely available not only in Japan but elsewhere. And then we have also the case of the 2011 earthquake, and we have the tsunami. So if you notice, the ASCE also included a chapter of tsunami in the years that follow. So I think, like in Japan, yes, they are very organized, yes, they are more prepared to have an earthquake, and they have this their own way of being resilient and of responding as a society, not as individual to event that is. I think that in the Western world, we are more capitalist, we are more individualist, so everyone is thinking about their own property. And it's not something necessarily bad, but it's the way it is. So it's very hard to convince the people, to act as a collective and not as an individual. So what do we do to raise awareness? In fact, nowadays, there's a lot of pressure to researchers and university to do more communication and dissemination of the results to the general public. Because if you notice and you go through our curriculum and see our CVs, we have a lot of technical papers that cannot be easily read, even by a practitioner. So this is why they are organizing these events. They are trying to go to school, attract the attention, talk to public, and raise this awareness. Unfortunately, people get only motivated when the earthquake happens. It happened in Italy in 2009 with the L'Aquila earthquake, and we had so many dead people. So a lot of risk communication, organization of events, and a preparation, like doing some mock earthquake exercises at schools, a lot of reading helps, but it's a big challenge. And this requires a lot of institutional enforcement. So the institutions locally and in the federal level, they enforce the code and they oblige, I don't know if this is very democratical, the people to take action and to protect their property and human life. So, yes.
Yeah, I know that's our challenge as an industry to make the public more aware before tragedies like that happen. And unfortunately, that seems to be the best motivator. But as an industry, we're trying to prevent that before any of that happens. But we are trying, and I know as an industry, we are trying to communicate to the public more, which I think is great with all these structural engineering institutions. So I think we are aware of that, and hopefully we are trying to communicate more publicly. I heard you talk about multi-hazard design. Could you talk about that a little more? I know I've heard it a lot of times, and I've used it when I was in grad school, but I know maybe some engineers didn't get through that or aren't too familiar with that term. Could you go explain that more for our listeners that aren't too familiar with that?
Yes, of course. It should be as simple as that. It shouldn't create any confusion. So what we have, usually what we study at school is single hazards, right? So one day in one module, we study the single natural hazard, that is earthquake, or it might be wind. And we can also study about floods, tsunamis, snowstorms, or we can study about man-made hazards, like blast, fires, and so on. So the scientists have gained expertise in all these fields, and then they realized that it can happen that the site, the building, and society is exposed to more than one hazard, right? Take, for example, Central America. We have areas that are subjected to moderate or small earthquakes. So it can happen that once in 100, 200, 400 years, or even 2000 years, they have an earthquake. And also it can happen that one in 100 years, they experience a wind. So they have to account and to design, and they have to take measures to mitigate the risk, right? And protect the structures against more than one hazard, multi-hazard. Now, where does it become complicated? The hazards may be mutually exclusive. So we don't have a hurricane hitting Miami, and at the same time, we have a huge earthquake in the same site, right? So they are mutually exclusive, and they can be studied separately, but they can be also interrelated. For example, if you notice the days where we have heavy rain, we have also high wind. So if we design for heavy rain, we have to consider the concurrent action of high wind. Or we can have successive events. It's true that we are talking about earthquakes as it's only one earthquake happening, but we have aftershocks. So we can have succession of events. In fact, we have scientists working on the effect of multiple earthquakes. So this is multi-hazard, the multi-hazard sub-principle of structural engineering, and yes, it's quite new. So the main idea that we follow in the multi-hazard design, what is it? The first thing, we identify the hazards, say wind and earthquake, the thing I'm studying in my daily professional life, and ask ourselves, are these hazards independent? I'm lucky in my case there are. What is the first thing to do? We apply those independently. So I run two computers to analysis in parallel, and I design my model. I simulate my wind response in one computer, and for the site, and for the same site, I simulate the seismic response. And then I do the design of the structure, and I'm trying to accommodate to have a good performance for the two hazards. I combine this performance, and I say, am I satisfied with the results? Are the combined losses that I get under a wind and earthquake scenario acceptable, or do I have to refine my design? So this is multi-hazard, that we have to think more than one hazards that are probable to occur at the same location.
That is great to kind of talk about. I'm not super familiar with multi-hazard design. However, I've been impacted by the lack of, I guess, appropriate planning. So when I was in Houston, we had the huge freeze. I don't know if y'all remember, but all of Houston, beautiful city that it is, energy capital of the United States, completely lost power due to a deep freeze. And there was a lot of conversations after the fact because we had this deep freeze that impacted our power grid completely. And Texas is very interesting because we're not connected to any other power grids. Like, they are fully self-sufficient in how they have built their power infrastructure. So there was no borrowing it from like neighboring states like Mississippi or Oklahoma or anything like that, because we are fully separated. But another thing that happened after that is, we lost complete control over transportation. So all of our roads were impassable because in the same respect, we don't have the appropriate infrastructure. It was never designed for a huge power grid outage, and then there's no way to pass through the road systems. Like there's no way to leave. So it's interesting that this is coming about and that people are starting to think about these things. And this kind of leads to my question is, in your opinion, what sort of multi-hazard, engineering strategies can be incorporated into design to enhance just like the resiliency and improve the robustness of buildings? Or, I mean, we can talk about buildings in particular, or we can talk about everything that structural engineers are involved in, which is, our road systems, our, everything. I would say civil engineering almost. There's a lot of things where structural engineers are responsible for the design, but I'm curious what you think about, maybe some strategies that our listeners could take into account.
Well, I think the thing that you pointed out would be the best strategies, like having in the same table people from different disciplines discussing about multi-hazard, because first of all, we need very good hazard scientists, and I'm sure there are plenty. So we need all the expertise that comes from the researchers, and then we need the input from the practitioners, and then we need the input from the stakeholders and the institutions, because we have all these consequences that come after the earthquake. That is not only the terrible human loss or damage, the property, the direct damage to the property. As you said, like for me, it happened when I was in 2011 and the earthquake happened. I wasn't in Tokyo at the time, but I couldn't communicate with my family. I couldn't go back to the hotel or the airport. I had in the embassy people looking for me. So all the society breaks down, and it's a huge disaster. It has like huge consequences. So first we need to have a holistic multi-hazard framework, that accounts and takes into account all these issues and tries to be prepared for the disaster and tries to minimize the cost. Now, if we want to be more particular, what are the strategies we incorporate? I can't speak because I have the expertise in earthquake and wind. This is what I'm studying now in my postdoc. So the first thing, be less conservative in the wind design. Why is this important? Because again, take the case of Montreal, or a city in central Canada or Central America that's affected both by earthquake and wind. It's okay if the earthquake dominates the design, is fine, because we can make a very refined structure that accounts for ductility, that behaves very beautifully under earthquake, and takes into account, its overstrength and so on. But if the building is a bit more flexible, a bit taller, what happens? We will have the wind dominating the design. And probably what will happen, this is what I've seen with typical steel structures, in Montreal, we will have to make the bottom stories more stiff, more rigid. So we will be changing the stiffness. And what is the result? We will be changing the design. But wait, the same model was used for earthquake. So we are changing, our lateral force resisting system. So we are compromising the very effective performance-based seismic design because of the conservative prescriptive wind design, okay? So we need also to reason in terms of performance metric and performance base also for wind design, and we need to account for both the hazard, no for the worst case scenario, because we need to be able to quantify the reliability of the structure. And also another thing, these are big countries. I come from Greece, I was in Italy, we have a dominant hazard, that was the earthquake. But like the US, the government in US or Canada should guarantee that the site that is influenced by earthquake is more or less the same safe, like another site that is affected by both a hazard. So we need some sort of coherence and consistency in the safety that we provide to the citizens throughout the state and the continent and so on. Yes, so more or less that would be my answer.
Yeah, thanks for that. Just to end off here, my last question was, what advice would you give to young engineers or even students who'd like to achieve similar success to yours, or maybe go on your career path as well?
Yes, okay, thank you. And I take that as a compliment, because I don't know if I'm very successful. I just do what I like. I like research, I like structural dynamics. And I was very lucky I was given the opportunity to have a postdoc in Italy and then here in Canada. My advice to the people is just be themselves and feel okay to be anxious. And it's okay, like as an engineer student, it's a very difficult field and you have to study long hours. Sometimes you have to skip the party or the friends and stay and prepare for your exams, but it's totally fine. And even if you feel that you're not the best student in your class, or you're not the genius guy who has the answer or girl to all the questions, or you don't have the engineering judgment, it's okay. There is place for everyone. What is important, and that this is something I realized through all these years, I'm 12, I think I'm studying engineering since 2002, so it's been like almost 20 years. Just be yourself, do what you like, and try to learn from the others, because building a big project is a teamwork. You'll never be alone, so you have to be honest. And I'm sure you have a skill, like each one of us has a skill that the person next to us doesn't have, so it's totally fine. So work as a collective, be honest to yourself, rely on your intelligence, but not too much. Hard work is more important than intelligence, because we need to be meticulous and double check. We don't want the structure to fall and go to prison. Be aware, you are responsible for someone's safety. And another thing that I wanted to tell to people, I never felt that I was a typical engineer, especially during my bachelor and first year as a research assistant, because I'm a girl and maybe I had different hobbies from myself and I felt I was different and I didn't fit it. But it's totally fine, you shouldn't be the average or what we consider the normal engineer. You can be anyone, you can do whatever you want in your free time and still be passionate about math and applied science. And another important thing, as an engineer, you don't have to be structural, a researcher, designer. There are many opportunities. You can be a policymaker, you can be a manager, you can work in the construction, you can develop software. I heard about a guy who did his PhD in wind engineering, and he was so passionate about algorithms that he ended up working for Facebook. So there are many opportunities. Just be open, talk to people, feel good with yourself. And it's very difficult, but it's worth it. So that's my advice.
Yeah, I think that's great. And yeah, like you said, I think you are successful because I think that's what everyone's trying to find. They want to work on their interests. And I think that's great advice in terms of, hey, you're interested in something and then you found a career doing it. To me, that's success. So yeah, definitely.
I know when you said that, I was like, you said that you weren't successful. I would argue if you're doing something that you really like, you are successful.
Yeah. It's important to wake up, and some days, I'm also not motivated. It's not easy, especially in research. And I think students feel the same. You might be stuck also in practice with a project, but then other days you see when your project is completed and you see it being realized and it feels perfect. So we just have to be patient and work hard, and it will be fine eventually.
No, that is great advice for our listeners, whether they are a student just entering the workforce or even if they're a long-term practice engineer. You can always switch things around and make life more exciting in the field of engineering, for sure. Well, thank you so much for your time, Anastasia. It was such a pleasure to speak with you.
It was a big pleasure for me. I would never imagine having the podcast. It's such a modern thing. I'm not very technological, but my family is excited and my friends, so I'm looking forward to listening to the podcast. And if anyone can benefit from the things I'm said, I will sleep better at night. I will feel I did my contribution to the engineering society.
Absolutely. It was a pleasure. And yeah, it's stuff like this that maybe isn't typical of engineers, but, thanks for coming on. I think it's just been great talking to more engineers, and for the people listening, I think it kind of does break some of those barriers and more communication with engineers, because I think especially when they're younger, they may not communicate too much, but I think things like this and you coming on really helps them out and actually gives them advice and things that they could be interested in. So I really appreciate it.
Thank you. Thank you very much. It was great talking to you, and I hope to meet you online or offline in the future.
Yeah. Thanks again.
For sure.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, which is episode number 65, as well as links to any of the resources, websites, or books mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all of your structural engineering endeavors.